pick a decent one, hopefully. So reactants make products, and you put coefficients in front of them. Okay, that's because there's a certain number of pieces of reactants that have to break apart and make pieces of products. The same number of atoms are on both sides, but what they're stuck to, just like your Legos when you're little, or still, can go together and make different things. So reactants make products. These coefficient things tell you the number of particles of each. I can spell particles. Okay, moles worth of particles, because they're so small we can't see them, but we can measure their mass. Remember, mass is in grams. So I can weigh out stuff. But remember, yesterday, one of those compounds was 342 grams per mole. Magnesium's 24.3 grams per mole. Really, really big, huge difference. You can weigh out the same amount and have totally different number of particles. Both of these had the same 6.02 times 10 to the 23rd particles. Super big difference in how much they weigh. Okay. So since weight doesn't work, we have to change them into moles. So you're going to be given a mass. You can write this down on something, I'm sure. You're going to be given a mass of something. You have to change that into moles of that something. How do you do that? You divide by the molar mass of that stuff, something. Okay, so that given mass divided by the molar mass. If you stopped there, you'd have number of moles of the given substance. That doesn't do you any good. Okay. The next thing you have to do is look at the balanced equation and see how the number of pieces go together. 3 pieces to 2 pieces, for example. It doesn't have to be the product, but I'm just, you're finding those coefficients from the balanced equation. That becomes your proportion of particles. And again, you can't see the particles, but they interact particle by particle. So this will give you a number of moles of the asked for. And the last piece, again, because I can't see the particles, that doesn't matter to me, the exact number. The next thing you're going to do is you're going to multiply by the molar mass of the asked for substance. So some number of grams. And that'll be your final answer that you need to solve for. In the laboratory, I can weigh stuff out, and I can weigh that I start with and what I end with. But everything interacts piece by piece, so I have to change it to moles first. So on this note sheet, it's the middle. It's just right out of your book. It's the middle part. Make sure that you have that on your notes. Remember, you can do a full page back and front of handwritten notes. And you'll have your calculator, and you'll have a periodic table, and you'll have your ion sheet and your reactivities. Okay? Questions? Yeah.
Can you go over the part one more time?
Yeah. So,
I got the for others.
Okay. So those coefficients, you got 2 of something, 2 of reactant 1 plus 1 of reactant 2 makes 3 product 1 and 1 of product 2. The coefficients these are telling you how many particles. Ouch. So when you're doing, let's just do a real one really quick. Not all the way through, but. Here's one you should be familiar with. 2 hydrogens plus 1 oxygen makes 2 H2Os. Okay, so 2 hydrogen molecules means 4 hydrogen atoms. 1 oxygen molecule, 2 oxygen atoms. 2 times 2 is 4. 2 times 1 is 1. So if I wanted to know if I had 8, excuse me, that's not going to, if I was trying to figure out hydrogen to make water, how much water could I make? Okay, I would put 2 for the hydrogen for every 2 H2O. If I was looking at how much oxygen needed to go with how much hydrogen, then I would do 1 O2 for every 2 hydrogen. I take the coefficients out of the equation. Okay, and then convert to grams using the molar mass and convert into grams using the molar mass. That makes sense? Sort of, on a Friday before it's going to be 100 degrees. It's going to be so hot at graduation. Oh my goodness. Thursday. It's going to be even hotter by then. Chico's going to be blasting. Yeah. I was driving up to my parents' house to do my wedding invitations with my girlfriend. We drove through Reading. 117. 117. And the air conditioner went out on my 72 Chevy Vega. No, it wasn't my Vega. It was my Subaru.
Our air conditioning in our house went out for like that one summer.
Oh.
It was really hot.
Oh.
So we would like go up to the car every once in a while.
Just to turn on the air conditioner. Just jump a bucket of water on your head. Yeah. All right. Yeah. Yeah. Hopefully. All right. So I'm going to stop there and get going with what I was originally planning to do and talking about skunks. How come you can smell a skunk? Everybody lives in Tuolumne County has smelled skunk before, right? Particles are in your nose. Exactly. Did we get to this yesterday?
No.
Oh, okay. Cool.
Like if you smell anything, it's
Because the particles are going up your nose. Ew. Ew. Don't think about that too long. All right. So it travels, right? The odor from the skunk travels because the gas that's in the atmosphere is moving really fast, even when there's no wind. It doesn't have to be windy. 2 categories of energy, KE and PE. Any guesses? That's on your paper. Good. So when you raise something above the surface of the earth, you give it gravitational potential energy. Potential energy is the energy of position. How high up above the earth determines how much potential energy it has. The farther you go, the more it has. That energy is stored and available to do work later, or get converted into kinetic energy if you cut the string, for example. Kinetic energy is the energy of motion. Moving particles have kinetic energy. Everything you will ever encounter is moving, including the table, including the counter, including everything you'll ever see that's not moving. The little particles that make it up are constantly in motion until you get to absolute zero, which we can't do, and you will likely never even get close to in your lifetime, okay? Unless you're a particle physicist, maybe, but you still won't reach it, okay? So this is, kind of physics stuff. More potential energy, no kinetic energy. They kind of exchange, right? You don't ever lose energy in the universe. It's all still here. It's just not organized anymore, okay? So this Newton's cradle thing, most of you have seen these before. If you haven't, you've had a deprived childhood. That's all I gotta say. So this one's not a very good one. It's not very balanced. But if I give one of these little spheres a lift, one goes out the other side. And again, it's not lined up very well. If I give 2 a lift, that's twice as much potential energy, and 2 of them will go. Try this side. Okay. If I give 3 of them, 3 go. And if I do 4 of them, any guesses? That's my favorite one, actually. So 4 of them, 5 of them, doesn't make any noise, right? So that energy is being transferred. It's not being lost. Some of it actually technically is, because you can hear it. That sound, that's moving the molecules in the air against your eardrum. Also, there's a little tiny bit of energy lost every time they touch each other. Do they feel warm? No, but they're getting a little bit warmer. Okay. So potential and kinetic energy. Moving things have kinetic energy. And it'd be fun to try, but probably shouldn't. Okay. Kinetic molecular theory and this is going right underneath the words kinetic molecular theory, not the bullet points. There's a couple bullet points here, but don't put anything there yet. Kinetic refers to motion, just like kinema is the root word. Cinema, moving pictures. That's where it came from. So an object has energy because it's always moving. Okay, the pieces that make it up are constantly vibrating. In a solid, they just vibrate next to each other. In a gas, they're flying around. In a liquid, they also go around each other. All matter is made of little particles. And the easiest thing to think about is think of gas molecules like BBs. Okay, so all matter, we're visualizing that matter has little bitty pieces that are running into each other. When you think about kinetic molecular theory, there's 4 assumptions that we make. And it's not perfect, but for all the circumstances you're likely to ever encounter a gas in, it works. Little small spheres like BBs. Basically no volume. The BBs have way more volume than atoms or molecules do. Always, always in constant, and again, we're back on gases, constant straight line motion. There's zippity-doo-dah across the room, smacking into the wall, exerting pressure, force over area, and then heading back in another straight line path until they run into something else. They have what are called perfectly elastic collisions. Technically, there is no such thing as a perfectly elastic collision. There's nothing perfect in the world, okay? But an elastic collision means that all the energy, they bounce off of each other, and all the energy stays with those objects. Okay, whatever energy they have stays with them. Real life, there's actually air resistance to slowing these down, okay? Still there? Yeah, okay. Good. All right, and then there's no attractive forces. So as those particles get close to each other, supposedly they don't attract each other at all. And that's because they have so much kinetic energy that they're just kind of flying by. Okay. Now, none of those statements is 100% true. Okay, it works good enough for everyday encounters with gases to make predictions, and we're okay with it. But in real life, it doesn't actually work just like that. So here's a picture supposedly of little BBs of gas flying around. The little kablooies are it's supposed to be when it hits the sides of the container. They could also hit each other like that one. Okay, and then they go off in a different direction, like pool balls or whatever else. Every time the little BB of gas hits a container, that's exerting a force over an area, creating pressure. You're under a tremendous amount of pressure right now, and it's not just because of finals. Every square inch of your body has 14.7 pounds of atmosphere pushing on it. Okay, that's a lot. That's like 2-gallon jugs of milk or whatever. Okay, that's a lot of pressure. You're used to it, so it doesn't bother you. But you certainly notice it if you go up the hill and your ears pop, or down to the valley and your ears pop. That's equalizing the pressure in your inner ear and your surroundings. So if it's really, really, really cold, or I mean like incomprehensibly cold, I'm not just talking like the freezing point of water cold, okay? 273 degrees below zero. That's absolute zero. Or super high pressure. If you squish, that's another concept that people don't really get about gases. So is this bottle empty? No, it's full of gas. Okay, it's not full of water, but it's full of gas. If I close this, I can still squeeze it. Why? The container is flexible, but also gases can compress, right? You've all squeezed a balloon before, you know what I'm talking about. So if you've ever gone up like to Dodge or something, had a bottle of water, come back down, you might find out that your water bottle gets all squished in. If you take a bag of chips up the hill, you might notice that it gets really inflated. That's because the pressure on the outside is less. Atmospheric pressure is tremendous. We're not talking 1 atmosphere or 2. We're talking hundreds of atmospheres of pressure, okay? Really, really big pressure, really, really low temperature. Then our kinetic molecular theory doesn't work. For every condition that you're going to deal with, it works fine. So again, atmospheric pressure is a big deal. Uh-oh. I think I ran out of water. Hang on. I may have to go get some hot water. That's still coming out. Okay, so I'm going to show you how much pressure that the atmosphere has. So this is a can that had water in it. And this is a dish of cold water. And so the water has turned from liquid to gas. I'm going to invert the can into the cold water. Oh, I can still see steam coming out. So there's steam in here, which is water gas. And if I do this, oh, it didn't come enough. Okay, I lied. It didn't work. Give me a minute. Oh, I know, bummer. All right, let me know when you see steam coming out of there again. All right, so empty space has what we call a vacuum. We're not talking Dyson or Hoover or anything like that. We're talking nothingness. Okay, very, very few particles per cubic meter. That's why if you're, in a jet plane and the window pops out, it's a bad thing. Okay. Atmospheric pressure, again, is happening because all those gas particles are banging into the walls of the container, whether it's the room, whether it's you that they're banging against. People didn't think that air was matter, okay, for a long time. But you guys know that you can feel it going past you when you found yourself, you ride your bike or skateboard or whatever, you can feel that rush of the gases going past you, creating pressure, okay? Atmospheric pressure, low pressures mean bad weather. High pressure, high atmospheric pressure, like we're going to have this weekend, means hot and dry. Gases will always fill the container that they're in to the best of their abilities. They'll keep going until they run into the walls, and then they'll bounce back again. Most gases are colorless and odorless. Bromine happens to be brown and has a weird odor too. Gas pressure, again, is a result of all those particles running into you, okay? And again, you're in this ocean of air. You don't notice it, but it's pressure on you as well. How do we measure gas pressure? We do it with a thing called a barometer. So there's lots of different units for pressure. Evangelista Torricelli was an Italian chemist, physicist. He worked with Galileo, and he was trying to figure out a problem, which we'll watch on this little video, about what's a vacuum. Can you have a vacuum? Is the vacuum sucking up the liquid in a barometer? You'll see in a second. Anyhow, this is a wood etching, an old print of a mercury barometer. Torricelli was the one to come up with the idea of using mercury instead of water. Prior to that, it was always with water because, of course, it's very abundant. This is a dish of mercury, and then that's a tube. It looks like a straw, but it's sealed. So they fill that up completely with mercury, cover the end, invert it into the liquid, and some of the liquid will fall in and make the mercury in the dish rise and then leave a gap at the top. As the atmosphere pushes on the surface of the liquid, it will change it. So one of the things that also people have a hard time with, and this is important to understand how barometers work. Everybody agree, gases are compressible, right? Are solids. Can I compress this table? No. Okay, it's not, because they're already touching each other. There's nothing, there's no space between the particles. Okay, so we got gases compress, solids don't. What about liquids? We want to say that. How many think liquids compress? I already gave it away. Anybody done a belly flop? Does it compress very well? It moves out of your way as you sink through it. But if you have ever done a belly flop off a diving board, you know that it doesn't compress. Why? Because the water molecules are all touching already. There's no room to go any closer. They're already touching each other. Gases, on the other hand, are 10 to 100 times their size apart from each other, unless they collide, okay? So let's just watch this little explainer on, hello.
Oh. With the bell ring.
Okay, thank you. So let's just watch this little clip. Please, not that one, bye. He's a friend of mine. Bloop. How are we doing on time? Bloop. And there it is. Takes me forever to find these. I'm sorry. I think I'd have it by now.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters.
10.3 meters. You guys know how big that is? That's freaking 30 feet tall. It's a 3-story building. That's really pretty tall. But if you're mining, it's not that tall. But to make a glass tube 30 feet tall, it's crazy.
With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box or the tube can have a heavy impact.
So the atmosphere pushes on the dish of mercury, and then that pushes the liquid that doesn't compress Doesn't have anywhere to go but up the tube. So 76 centimeters is 760 millimeters. That's the height of a mercury column at 1 atmosphere pressure. 10.3 meters is about 32 feet, and that is the height of a water column due to 1 atmosphere of pressure. All right. So how much pressure is that? Well, it's quite a bit, actually, and I'll show you that in just a second. I don't see any steam coming out of my can yet, but it's making noise. So again, high pressure would push on the surface of the liquid, which would push it up. A lower pressure would allow the liquid to column to fall back into the tank. This is an old style barometer that was used on sailing vessels. This little spigot right here is open to the atmosphere. And so if atmospheric pressure is high, it pushes the water down the spigot and back into the chamber. If atmospheric pressure is low, like it would be in this particular picture, that's an indication that bad weather's coming and sailors take warning. This is an image. It's not ours, but we have one exactly like this, the same wooden case and everything in the back room. There's a dish of mercury at the bottom and then a long tube, 76 centimeters, that has like a straw basically into that tube for measuring barometric pressure. There's other ways to do pressure besides liquids. You don't need water. You don't need mercury. Some of you may have these, or your grandparents may have dials like this in their office at home, and some small private planes, like little Cessnas and stuff, use aneroid barometers for altimeters. Why? Because lower atmospheric pressure at higher elevation, less atmosphere, less particles of gas. And so they have like a little balloon inside them, like a little cushion, air cushion. And so when atmospheric pressure is higher, it squishes the balloon, causes little mechanism to spin the dial. When atmospheric pressure is lower, the balloon can expand and it spins the other way. The unit for pressure is the Pascal. You should make sure you write that down. That's the SI unit. Because it's so small, we use kilopascals, thousands of pascals after Blaise Pascal, the guy that took it up the mountain. That is 760 millimeters in a mercury barometer. It's 101.325 kilopascals. That's 1 atmosphere of pressure. There's tons of atmospheric pressure units, which is really confusing. There's torr, named after Torricelli, which just correspond to millimeters of mercury. Millibars, if you're a meteorologist, inches of mercury in this country. If you look on the side of your tire, 14.7 PSI, pounds per square inch, is 1 atmosphere. Your tires on an average car are usually 32 to 35 PSI. There's lots of other units, but those are the main ones. And then 1 atmosphere. We talked about it. 1 atmosphere of any gas at STP, 22.4 liters. What else? Higher the temperature, the faster the particles move. Just think about it. You put your hand on the stove. Ouch! You move really fast, right? No. One of the things on pictures you'll see is longer tails. That means they're going faster. Pew, pew, pew. They're bouncing off the walls. The more times they hit the walls, the higher their average kinetic energy. Important point. Higher temperature, higher kinetic energy. The hotter it is, the faster the particles move. If they move fast enough, they can shake apart from the solid to the liquid to the gas. The average is somewhere along the spectrum. Even the coldest sample has high kinetic energy particles. Even the hottest sample has particles with low kinetic energy, just that the most of them are going to hang out together at the average. You've seen water crystals form in food that you had in your freezer. How did that happen? The frozen water became a gas and then it refroze. And Kelvin is the guy that came up with absolute zero. He is the one that came up with that. And absolute zero is 0 Kelvin, no negative numbers on the Celsius, on the Kelvin scale. Okay, hopefully this works. Ready? 1, 2. I think it's hot enough. Oh, yes. Okay, I did not squish it. Okay, that's as squish as I can get. I did not do that. So this squished because the gas inside got cold, and then it became a liquid water again instead of air. And the air on the outside has atmospheric pressure and caused the can to squish. Oh, we made it. Sorry. I'm exhausted. Are you guys exhausted? I'm exhausted. There's lots of other stuff we could talk about. I'm sorry. We didn't get to everything. It's the way it goes. Thank you for your patience this year and for being so kind. All the time. Everybody, have a nice weekend. Be safe. Be good. Bring your cheat sheet. Bring your calculators.
I just want to make sure these are going to be put in for the grade book, like the lab molecular model.
Yes, they're sitting on my desk.
All right.
I promise they will. You too. Thank you. I'm so sorry. I just am so far
Oh, that's
behind.
all right. Don't worry.
Having to make up new stuff constantly. I cannot keep up with everything.
'Cause
Thank you.
I just want to make sure everything gets in because
It will help your grade a lot.
everything that I turned in,
You get good
late
scores.
and everything, it should put me up to a C.
I'm hoping that will be the case.
Alright.
I'm hoping so. I was surprised to see that your grade was that low. So, yeah.
Me too.
So, yeah, just